Okay, so what I'm going to do today is I'm going to start looking at how we actually solve the equations. In other words, we wrote down the geodesic equations the last time from the Hamiltonian formalism, and we basically started from our scalar function, the Hamiltonian. We defined this entity called the Poisson brackets, which was simply, in some sense, applied to two fields of conjugate momenta and conjugate coordinates and momenta, or generalized coordinates and momenta, and it was simply defined as this derivative of mixed partials where there's a subtraction sign in between it. And this appears in many other places beyond just classical mechanics. It's a structure that they sometimes also call the symplectic structure. And then I said, Hamilton showed that all equations of motion for any mechanical system that had this conserved or this energy could be written in terms of our Poisson brackets. And then I went and I said, okay, fine, we're going to look at the general relativistic case. We're going to have basically 4 degrees of freedom, so our 4 fundamental variables or coordinates, time being one of them, which basically corresponds to there being 8 variables, because with each coordinate there's a generalized momenta associated. And so what this means is then we have basically 8 differential equation with 8 first order equations. We have it's homogeneous in the sense that it doesn't depend on the parameter tau, or autonomous, it doesn't depend on the parameter tau. And we said that the Hamiltonian that we got, we could actually just make from metric functions. So at the moment, this is the only place where GR comes in. It tells you what these functions are, and it had this general form. Okay? And then I said that's still too complicated, because for a large part, if we're just working with 4 by 4 in the full 4-dimensional space-time, many cases this thing is only known numerically, so we're going to then specialize to our SAV space-times, where we assume that rho and phi aren't there. They're not in the metric functions, and so our metric functions is only in terms of rho and g. And we're then further going to assume that we're working in a vacuum. And if you then look at all possible space-times that have that solution, you can write the metric becomes even more restricted, with a lot of the metric functions being equals to 0. And you actually can find, I have not given it to you, but you can find the form of these metric functions explicitly. And those are the class of all the systems that you can potentially play with. Okay, so that's your restricted sandbox for the next 2 years. So we're going to look at a whole bunch of systems that come from there. And when I further went on and I said, let me now write down the equations of motion just using Hamilton's formalism, and then what I got was basically Q dot is GH dP, and so that's how all the coordinates change in time. So you start at a specific spot with a certain vector, you integrate it, and how that position changes is how your coordinates change, how the vector changes is how these momenta change, and you can actually solve those equations. And what I'm going to do now is start going further beyond just the equations. We've written them down. You should write them down for either Schwarzschild or Kerr, that you just get a feeling for it, because Kerr is the one that we used in the paper with Marissa. Schwarzschild is also basically the Schwarzschild result is a limit of Kerr. So it's very useful to have the limit so that you can compare the two. So that's what I was hoping that you would do. What I now want to go on is, once you've got these equations, I want to say what else you can say about Hamiltonian systems in general. When are they chaotic and when are they not, and what type of computations we can do with them. So just one thing is, remember I said, look, we've integrated the PT and the P phi already, because we knew that PT dot and P phi dot were equals to 0. In other words, they did not change with the parameter. And the reason they were 0 is that the Hamiltonian did not depend on phi and t. Okay, so in some sense, when we took this derivative, this became 0, so you could integrate the equation. So those are constants and makes life a lot simpler. And then we also said that this t dot and phi dot, okay, depend only on the constants. Remember, pt is a constant, p phi is a constant, so those are constants, and on rho and z as a function of t. So these two decouple from these bottom four. Okay, so the thing is basically we can solve these bottom four, which is going to be the focus of the this lecture, or the beginning focus of this lecture, the way we think about solving it. And then after we've got the answer, we can put it back in and try and get these two out. Okay, so it makes it a simpler, both numerically and from the point of view of doing analysis of the problem. And then the last thing I said, and I'm going to actually come back to this, is you can show that h dot equals to 0. I said in this case, you could simply write out what h dot is and then substitute these equations. I'm going to show, at least in the limited case of the 2 degree of freedom system, this is true for any Hamiltonian system that doesn't explicitly depend on the parameter. So any Hamiltonian system where there's no function of tau on the right-hand side, this is true for, and I'll prove it to you now. So you basically have h dot is equals to 0, and then we get that we have p rho squared over g rho rho plus pz squared over gzz is equals to a function of just constants, okay, mu being your Hamiltonian constant, and minus a half mu square being your Hamiltonian constant, and your position vectors. Okay, so that's where we were the last time, and the question is, how do we go further? Okay. The first observation I can make is, if you look at the way this thing is written, okay, if you consider Lz and E just to be constant, you can actually define a new Hamiltonian that's just a function of rho z, p rho, and pz, okay, and solve that one. So you can actually look at a smaller or a smaller degree of freedom system and solve that one, and then the answer will actually give you rho dot and z dot. You can write down the Hamiltonian, which will just be this thing minus, basically minus this part over here, and that will be a Hamiltonian in basically rho z, p rho, and pz. Okay, and you can do exactly the same, write down the equation of motion, except now that these things will be parameters in your Hamiltonian. Okay, so what I'm going to do now is look at just 2 degree freedom Hamiltonians, because it's simpler to write it out and it's also easier to actually sort of wrap your mind around it, at least the first time around, and then look at some of the results we can get there, and also give you an idea of what we're aiming for if we want to say the system is integrable. In other words, the orbits are nice and organized, and the system, or if the system is chaotic, because those things are possible. Remember, we have 4 equations. We need at least 3 to get chaos. So the possibility of chaos existing is very real. And so what we're going to do is define what we mean if a system is chaotic, or if it is in fact integrable. Okay. So let's now look just at 2 degree of freedom systems. So by 2 degree of freedom, I mean a Hamiltonian of rho z, p rho, pz. And once again, this is a general Hamiltonian. So what I'm saying is true for any Hamiltonian system. Okay. What we then have is, I just want to show you that the Hamiltonian is conserved in general. Okay. So the way we do that is we work out h dot, okay, and we simply say that's dh dp times p dot plus dh dz times z dot plus dh dp rho times p rho dot plus dh dz times pz dot. So it's just the chain rule and we're taking the complete derivative with respect to tau. Okay, questions there. Right. What we then do is we replace these dots, the dotted entities or the entities that I'm taking the complete derivative with respect to tau of, with the equations of motion, or Hamilton's equations of motion. So I'm going to replace everything p mu dot with q mu dot with dh dp mu, and p mu dot with dh dq mu with a minus sign. Okay, and so let's do it. There you can see we have replaced p rho dot and z dot over there, and now we're going to have p rho dot and pz dot, and the minus sign becomes important. So there I've replaced p rho dot, it's just dh d rho with a minus, and pz dot with just dh dz with a minus. And if you look carefully, this guy cancels out with that guy, and this guy cancels out with that guy. So you can see why, in general, your Hamiltonian is conserved. It's one of the very nice structures in your Hamiltonian system, because your first quantity that remains constant along your trajectories is given to you, provided you don't have a tau in the Hamiltonian itself. Okay, this is the generalization of the conservative system that Strogatz does. So when Strogatz did conservative systems, what he was basically doing was a Hamiltonian with 1 degree of freedom. Okay, so this just generalizes it further, and this is the proof. You then have h equals to hc, which is a constant, and for gr I call that minus a half mu squared to fit in with all the physics people were doing with it later on. Okay, so that's a general proof of your Hamiltonians conserved. And so what I want to do now is think about this thing geometrically, right? We have a trajectory of rho, z, p rho, and pz. So we have 4 coordinates in this 2 degree of freedom system. And in some sense, it's our like generalized space of coordinates and momenta. And when we solve the differential equation, we're going to have a curve moving around in this 4-dimensional space. Okay, and what it means if you have h, a quantity that's constant in the 4-dimensional space or doesn't change along the curve, it means that the trajectory cannot go everywhere in the 4-dimensional space, but it must remain on the volume defined by h equals to hc. Okay, you have 4 coordinates, you have one function that has to be constant, and so that basically restricts your orbit from moving anywhere in your 4-dimensional space to an orbit moving on a structure, in this case a volume, with dimension say 4 minus 1. Okay, so that's what the Hamiltonian does. Okay, in some sense it's a simplification of where your orbit could possibly go, and it's also a description of what this orbit in phase space does. So now the thing is, suppose I say if, and this is a very big if there exists another function, in other words, another function of pz, p rho, and pz, such that along the trajectories its derivative is also 0, okay, then it can tell us something else. I'm not saying it exists, I'm just saying if we can find it, then we've got another very useful tool. Okay, and very importantly, this function must not be a random function of h. In other words, you must not be able to just say q cannot be, say, an exponent of h, because that's constant, obviously. Okay, so this function cannot be a function of h, and a way you can check it that it's not a super sneaky function of h is you can simply take the gradient of q and the gradient of h and take with respect to all these coordinates and take their curl, and if that's 0, then you're sure. Then it's an independent function. Okay, so the gradients of q and h cannot be parallel. That's just another way of saying it. So if you can find this function, and you can say that q dot is equals to 0, then what you have is that along the trajectory, you also have that q equals to constant. And what that means is that the trajectory is stuck not only on a volume, but on a surface. Okay, so 4 dimensions, you have 2 independent functions mapping those 4 dimensions, or sort of restricting those 4 dimensions. And what that means in practice, that the trajectory in your 4-dimensional space is restricted to a surface. Okay? And what is nice now is it's very hard often to find Q. Okay? It does exist for some spacetimes. And I spent a lot of time trying to classify all of them that it does. But if you've got it, then you have a very strong restriction of where the orbit goes, and in fact, you can integrate the orbit completely. Okay, so the question now, or the first question is, how do you know if you have to go looking for it? Because generally, to go looking for it is tricky. It's very difficult. There's no set of rules for finding these things. There are a few things you can try, but generally, you have to have some reason of guessing wisely. Okay, so one way of checking it to see if it exists is you take the equations and you integrate them. Okay, and think about it. If you have a surface in 4-dimensional space, and then you take a slice through that 4-dimensional space. Say, suppose you put in a slicer, and I say, I want to look at this 4-dimension of the surface in 4-dimensional space whenever it crosses the plane z equals to 0. What I then do is I'm either not going to cut the surface, or I'm going to cut the surface in a closed or in a curve. Okay, so while 4-dimensional space is very difficult to visualize, what you can totally do is integrate the equations, look at them every time z is equals to 0, and if all those dots line up onto a curve, then most likely then it's at least possible that the trajectory lies on a surface, and you can go looking for constants of motion. So it's a numerical check to see if you should start looking for those constants of motion. We also say if Q exists, so remember when we did the 1 degree of freedom, we said that if we can find that conservative quantity, then we can write down those potential contours, and the system is integrable. The same for 2 degree of freedom systems. If you can find 2 conservative quantities, basically H and Q, then you can say the system is integral, there's no chaos. Okay, because you know exactly where the orbit runs. And because it runs on a surface, and the orbit can never cross itself, you can actually define exactly where it's going to go. So, okay, so the way to look for is to say if you have z equals to z0 slice, where z0 is a fixed constant, then the surface becomes a curve in 3 dimensions. Okay. So you can remember, if we also go back to Strogatz, when we looked at the pendulum system, there was this idea of how we proved that you had a limit cycle. We had this idea of looking at the orbit, as say when theta is equals to 0, and then looking at the value after 2 pi, and then looking after the value after 2 pi again, and we made that map that I called the Poincare map. There, this is the generalization of the Poincare map to 2 dimensions. Okay, so I'm just going to summarize. If you basically want to make a numeric check of whether Q exists, and I'll illustrate it again on the next slide as well. So the numeric check is basically first integrate all your equations of motion, in other words, the rho dot z dot p rho dot pz dot, and find basically a numeric version of what these trajectories are. In other words, if you put them into MATLAB with ODINT 45, you're eventually going to get,
So is this now the time parameter or the tau?
There's a mistake, yes, it should be tau. I apologize, yeah. I don't know how that slipped in. Yes, definitely that should be tau. Okay, very important, thank you. And that should also be tau. So somewhere I had Okay, a sleepy moment. Okay, so anyway, you integrate it and you get them as a function of parameter tau. Then then you say is, I look at this, so I've basically got vectors of all these things. I'm going to look at the z vector, and I'm going to find every single point at which z of t is equals to a constant. Okay? I'm going to throw away all the rest, and I'm going to keep those points for parameter tau, where z is equals to z0, and I'm going to keep the other values. Okay, so I'm going to record p rho, pz, and rho over there. Then what I'm going to do, and this I can do in general, is I'm going to check that the Hamiltonian remains constant, because we've proved it must. If it doesn't remain constant, basically your integrator is broken or you've made some other mistake. So it's a sanity check. The first thing you do is simply make sure that the Hamiltonian of this integrated system remains constant. Because it's numeric, it won't be exactly zero or exactly constant. You'll have to say it's got to be the value you expect within a tolerance that is set by the tolerance you've got on your integrator. Okay, so if you're integrating the like p rho, pz, and you tell it that it mustn't make an error like bigger than 10 to the minus 14 or so, then you expect your Hamiltonian to be conserved to like 10 to the minus 10. Okay, so it's not going to be exactly right, but it's got to stick close. The moment it starts departing very largely from like with 2 or 3 significant digits, you made a really big mistake. There's something really wrong. And then you've got to find it before you go on. Otherwise, you are talking nonsense right from there on. Okay. So you first check that the Hamiltonian holds. Then, remember the Hamiltonian can basically give us pz. Okay, the Hamiltonian is a function of p rho, usually p rho squared, pz squared, and a whole bunch of the other stuff. So if you know what z0 is, then you can find pz using the Hamiltonian. Okay, so when you plot things, you don't actually have to plot pz because you always know what it is from the Hamiltonian. So what we plot then is simply p rho versus rho. Okay, and if the points sweep out a curve, then you know it is possible that Q exists. It doesn't mean it does exist. It means that it's at least possible. Okay, so it's a thing that goes one way. Q existing implies that you will have a curve a curve when you slice your 4-dimensional space. That's true. But the reverse, saying that you appear to have a curve numerically, doesn't prove that Q exists. You still have to find it exactly, but it's at least an indication that it doesn't not exist. Okay, so there's that subtlety. So the arrow only goes Q exists to it's a curve. Seeing a curve numerically says you can at least look for Q, but it doesn't prove that it exists. Okay, so if you see a curve, it's go look for it. And here's a quote from Marsden, who's an atheist. He's now deceased. He was a professor of dynamical systems at Caltech. He wrote a very big book on symplectic structure, which is sometimes another way of looking at the Hamiltonian structure. Also, one of the best books is Goldstein, for the purposes of it being readable and explaining things very nicely. And a lot of this stuff is Goldstein condensed. Okay, so it might be worthwhile to get Goldstein out of the library. It's quite old, so it should be in the library. There are a lot of PDF files. Get yourself one. Because if you want to look things up and just look at other examples beyond what I'm focusing on, it's very useful to have. If you're going to solve a mechanical problem, it also has a lot of tricks and a lot of problems are actually solved in it. So it's highly recommended. Anyway, the textbook after Goldstein is Marsden on the symplectic structures. He does it a lot more mathematically, but he hides a lot of the beauty if you're reading it for the first time. And his comment was, basically, if you want to go looking for Q, what you need is luck, skill, and prayer. And yeah, given that he was an atheist, you can get an idea of how desperate he was. But that's the thing. Okay, so now the next one is, if the points randomly scatter when you do this program, namely, you work out your orbit and then you look at everything when z0 is equals to 0, okay, and you plot p rho versus rho. If the points scatter randomly, in other words, they aren't restricted to a nice neat curve, that is proof that you have chaos, Hamiltonian chaos, okay. That means if you've done numerics correctly, and it's worthwhile checking first of all that you've actually done that, because they'll scatter randomly also if you've made a sign mistake in one of your equations. Okay, so if you've done the numerics correctly and the points scatter randomly, then you know basically you have Hamiltonian chaos. You also know that it is impossible to ever find a function q distinct from the Hamiltonian such that q dot is equals to 0 along the trajectories. Okay, so this is a very nice game, which I'm hoping that you're going to do at least once or twice, because it's something you can do in other systems too, and it gives you a very clear indication of what is actually going on. One of the first places that it was actually done in this form is by Henon Hylas. They had a problem of a star moving in a potential, moving basically around the Milky Way. So most of the Milky Way stars are stuck in the horizontal plane, okay? But every now and then you get a strange star that is orbiting not in the Milky Way plane, but round like that. It's like orbiting at an angle to this disk. And they wanted to study how the star would move under the influence of the disk. And they wrote down they found their Hamiltonian, which is all we care about for now. And they believed, at least before this century, most of the people actually believed you would always be able to solve the problem. In other words, that Q would always be found. Very few people looked at problems in which Q didn't exist. And only when we started integrated numerically did we actually start looking for problems where Q is absent. And we started studying that in greater detail. Anyway, when one of the first guys was Henon Hylas. So they wrote down the Hamiltonian, and then they integrated it, and it went random. And eventually they worked out they plotted this version of the Poincare map very, very nicely, and they showed how it broke down. Okay, and we can do a similar thing in fact, I've done a similar thing with some of these space-times, and we can actually look at them if you find one that's interesting to you. Okay, questions here? Not yet. Okay, so I just want to illustrate it to you. So this is a space-time that actually my previous master's student worked on. We didn't actually end up publishing it because we never got to the place where it was sort of complete or far enough, but this is a space-time. It's called the Zipway Fourier metric. It's basically, if you think of Schwarzschild, that's just the space-time of a point mass, okay, like one dot. This is the space-time that you get if you have like a rod. Like suppose you have a rod that's not just a spherical sphere. You have a rod, and then you look at the space-time around it, then it's a Zipway Fourier metric. And you can either take the rod and extend it. It's got a parameter delta, which is part of the metric. You can either make it flat and skinny, or you can make it like a disk. And depending on what you do, you get a different space-time, and the orbits deform. And the reason I studied it is because it's simple. In other words, I could actually work with the metric functions quite easily. And so I just want to illustrate to you like the quantities that you were looking at. So remember that Hamiltonian constant. It's also space-time in which the metric element with respect to rho and z is the same. Okay, so it's also simpler from that point. So remember I had that p rho and pz equals to a constant. So, p rho over g rho rho and pz over gzz is equals to basically constants plus functions of rho and z. So here that thing is, okay? So you basically have your momentum squared equals to some function j of rho and z and the parameters that we put in. And this function j, the contours of it, I've plotted over here. Okay, so you can literally think of it as a particle moving in like a thing that has like a little well over here, and then it falls away. Okay, and so if I then integrate the Hamiltonian equations, various things can happen. So suppose, oops, no, I didn't want that just yet, sorry. Suppose I start over here, in other words, here, this thing is just a valley. It's basically all my kinetic energy, it's going to start even from zero kinetic energy, it's going to basically roll into the black hole and crash with it. Okay, so you can see all these cyan trajectories simply roll down this potential into the black hole and crash with it. If you start over here, like way back, okay, say over here, what's going to happen is it's basically going to roll down this very steep wall, then go over this little valley in the middle, and then crash into the black hole. Okay, but if you start here in this middle, it's actually going to get trapped. Okay, so it's going to, just like that double potential well that Strogatz does, it's going to get stuck and it's going to wander around this potential well, and this is the orbit that it's going to do. This is an example, this is an example of an orbit. Look what I've plotted here. It's just z, and z is typically, on the axis that does this. It's actually an angle. And rho is the distance from the origin. It's going to basically, in rho z, it's going to do this, but in phi, it's also going to go down. So it's like one of those very organized orbits that we saw with a Manco movie, where it actually moves around, and as it orbits around the black hole in rho z, if I just project it onto rho z, it's going to be doing this. Okay. So you'll get a feeling once you do the first one of what these plots actually mean. So what I've done here is plotted just the z of tau versus rho of tau of this particular orbit. And so what the Poincare map is basically is I'm going to now look at this orbit whenever it crosses z effectively equals to pi over 2. Okay, so I'm going to go in and I'm basically going to say of the orbit, I'm only going to look at the points when z equals to pi over 2, so which is close to 1.5, and for this physical case, that's when it's crossing the equatorial plane. And then what I'm going to do, whenever it crosses, I'm going to simply record what p rho is at that point versus rho. Okay, so the orbit that's shown there in red is actually this curve, these dots over there. Okay, so what's going to happen is, suppose I start over there on the equatorial plane, okay, then I'm going to get one dot, say at rho equals to 3 on the equatorial, at p rho equals to 0, okay. Then it's going to basically oscillate up, reach a maximum z value, then it's going to come down, and it's going to hit it over there, okay. And then I'm going to basically plot that, whatever p rho is then, and it's going to be moving quite fast. And then I'm going to plot it on this plot. So the rho is going to be sitting somewhere, some large value over there, and say it's going to be that dot. Okay, so this curve doesn't sweep out. It like the dots jump. When you make these plots, the dots will jump around the curve. Okay, and then you go to the next one. Then over here, it goes down. It hits that sort of the maximum value, and then it say comes up and it hits it over there. So you're going to have another dot over here, and then it's going to go all the way up and come back down here. So you're going to have another dot over there, and it's kind of cool to see this thing form itself. Okay, so that's what the Poincare map is. And then this blue one was another orbit, but if I also plotted it gets confusing. There I say started over there, and then it had a different, it sweeps out a different line. But you can see that all the different orbits seem to lie on a curve, and then you go and you start looking for Q. And this is actually why I looked at this problem, because it seemed easy enough that I could try and guess it. And there are various techniques that we may or may not go into how you guess Q. And anyway, the actual lines I've drawn in here are actually my best guess so far. I think I haven't published this at all, but it is a guess for Q. So if that's something you're interested, you could go on and do some of that, and we can see if we can actually get somewhere with it. What is interesting of the system is that, and that's where Marissa's work actually came in, is that there isn't an exact Q. So even though the orbits seem to lie very, very close on this curve, I know that there are places where they don't and where they actually break down. So I'll never be able to find a Q, but I've managed to get a very good approximation for Q. Okay, so this is kind of an example of where the orbits look integrable in the sense that they are lying on exact curves and you can check for it numerically, but it doesn't mean that a Q exists. But for all practical purposes, in this case, you can basically get an approximate one and calculate with it and learn a lot about the system, but it isn't exact. So this system, strictly speaking, isn't integrable. Okay. Yes?
So on the plot there with the red lines, does it stick to that say flat level, or does it go into the bump there on the top and at the bottom, or is it?
This orbit doesn't. This is, I simply integrate the equations and they stick in that box. Okay. If you were to start the orbit on the equatorial plane over here, okay, then it would actually go up higher into this. So this bump is what I call the allowed region, right? And this bump is caused by, look at this equation. The black curve is what I call the boundary of the effective potential. Look at this equation. We have our Hamiltonian constraint that requires that p rho squared plus pz squared equals to some function over here. And this is a positive or zero, okay? And it's dependent on the momenta, so you know your orbits are going to be confined to the region where this j is equals to 0, okay? And the j equals to 0 is what I call the effective potential, and that's this curve. Okay, so all the orbits have to stick inside that curve over there. Okay, and in fact, these are the contours as j changes. Okay, so all the orbits have to stick inside this contour, so that they all do. But the individual orbits all seem to make themselves into little boxes like this. And but they can get like, if you start one over here, and it's actually a very nice thing to play with once you start doing it. If you start an orbit over there, it's going to make a long and skinny box that's going to go deeper in. And it's simply going to stay that. And in fact, here's a very unique orbit that I can find, that you can find numerically, that just goes up and down. Okay, it's the skinniest one of them all. It just goes up and down. And what that is basically, it's your circular orbit. In other words, the orbit that does not change, or rho doesn't change like this red one does. It's roughly rho dot is equals to 0, so rho is effectively a constant, and that's the skinniest one that you've got. Okay, so eventually you can see how they arrange themselves into a structure. Okay, so let's just one more thing, define a little bit more mathematically, so that when people talk about this, what we've done. So we've already seen that I'm going to define what a cyclic or ignorable coordinate is. So now we're going to call it ignorable for a while, and you'll see why it becomes cyclic later on. Okay, so a generalized coordinate qi is said to be cyclic or ignorable if it is explicitly absent from the Hamiltonian. Okay, so for example, in our four-dimensional example, t and phi, that we basically assumed weren't in the metric and therefore not in the Hamiltonian, we're cyclic and ignorable. If you want to go, you can go. Huh?
I was waiting 5 more minutes.
Okay. I've just got one slide, so it'll be fine. Okay, it's cyclic or ignorable. If it's absent from the Hamiltonian, its equivalent dH, dQi is 0. Oops. Okay, and you also have that if Qi is cyclic, then P dot is equals to dH dQi is equals to 0. And so therefore you have that P is equals to a constant. Okay, so every ignorable coordinate has a momentum that is constant. And now the game is ignorable coordinates in H given automatic reduction of the equation degrees of freedom, just like we went from 4 dimensions to 2, because we could put the constants into the Hamiltonian instead of the momenta. Okay, so that's a reduction of the number of degree of freedom, and if all the coordinates are ignorable, in other words, H is a function only of the momenta, not of position, okay, then what we have is that Q dot I equals to H dPi, okay, but this right-hand side is a function only of these constants that appear, okay. So the h dPi is a function only of the constants, and therefore it can be a random function of the constants. That's not been said. But what we do know is that it's a constant itself. Okay? And then we can solve it, right? So then you basically have Q dot equals to some constant. You integrate it. So you have Qi equals B dot T plus some constant gamma I. Okay? And this, remember I showed you the last time the idea of trajectory running around the torus, okay? This is what it is. It's a very convenient system in which you can label the trajectory with these constants bi, and they're just going to run around the torus themselves. And I'll come back to this again later on. And so the holy grail of dynamical systems, if you want to solve it exactly, is to change coordinates so that all these coordinates become cyclic. So you actually want to change coordinates in a way that your Hamiltonian becomes as simple as possible. Okay. And that's going to be the topic of the next lecture. And it's how you do it. You basically have to change both your coordinates and your momenta. And how you do it, what is known about that is kind of interesting, and it forms the core of Hamiltonian mechanics. Okay, I think I'm actually going to leave it there. I've got one more thing to say, but I'll wait for the next time because I'll use it then as well. So thank you very much. Let me just stop the recording and then ask you a question.